There are two types of tidal energy recovery devices, tidal barrages and tidal stream generators. This lecture will cover the ability of tidal barrages to recover energy from the tides. Let's begin with some definitions. There are really three key components of a tidal barrage: the barrage itself, a turbine generator set, and a sluice gate to control the flow in or out of the tidal basin. So in the drawing shown here, we can see this semicircular, semi-elliptical shape here represents the shoreline of a bay or a tidal estuary. A tidal estuary is a river mouth that enters into a bay which has a strong tidal flow. So you can see if we have this bay, we can build essentially a dam across the opening and create a tidal basin, which is right here, to capture water from the tidal flow. Of course, the sea is on the outside here. So the sluice gate controls the flow in or out of the tidal basin, and then the turbine is connected to both sides to allow flow in one or both directions depending on the type of system, power generation system. The fourth element of a tidal barrage comes under the category of accommodations, and so things that fit in that category would be a lock to allow ships to pass. So if this is a harbor which supports fishing industry or leisure activities, there has to be some provision for the ships, and also the environmental aspects of allowing a flow of fish back and forth. Okay, now the simplest way of generating power from a tidal barrage is to allow the barrage to fill on the flood tide. So the flood tide is the tide coming in. So here's the fill cycle right here. So we see the tidal basin in cross section, the seaside here, and then looking at the top view you can see the sluice gate is open here, and so the tidal flow is coming in, and then once the tidal basin height has been raised to the high tide level, as the tide falls, then the difference between the two heights allows water to flow back out through the turbine and generate power. So during this period the sluice gate is closed. A more complicated arrangement is to try to capture the power in the tides on both flows. So generating on the flood tide, so here we see again from the seaside there's a different height that drives the flow through the turbine, so that water flowing in the flood tide is coming into the tidal basin through the turbine. The sluice gate is closed. And then on the ebb tide, so the sea level is falling now in the tidal basin, there's a differential height here ahead which drives the flow through the turbine. Now the flow is coming back out through the turbine to produce power, and the sluice gate is again closed. So in this case you're generating power on both the flood and the ebb tides, whereas on the ebb generation system you're only capturing the ebb tide. Okay, so in order to evaluate how much energy can be recovered in a tidal barrage system, let's think about the potential energy that's stored. So it's really about the tidal basin captures potential energy. So if we look at a tidal basin here, this upper picture shows a low tide in profile. So we have the seaside here, the tidal basin in this area, and we have a surface area on top of this water, and then we have the high tide shown on the bottom picture. The bottom red line marks the low tide height, and then this represents the upper height, so this is the tidal range, capital R. So what we want to do then is to look at the potential energy of a differential mass. So this would be a thickness dH here, and its volume then is dH times the surface area S. That gives us the volume, and we multiply that by the density, gives us the mass, and then the potential energy is GH, or the differential potential energy, as GH times dm. So if we put all this together and integrate it from 0 to the tidal range R, the maximum difference between the low and high tides, we come up with 1/2 rho, where that's the density of seawater, times the acceleration of gravity, times S, again the tidal basin surface area, times the tidal range, the difference between the low tide and high tide, the maximum difference, squared. So now when you look at this equation up here, you can recognize that S can in fact be a function of H. I've assumed for this simple example that it's not, but one can readily put in that functional dependence and integrate and get a slightly more refined equation. For our purposes, this is perfectly adequate. Okay, so let's consider a single tidal flow now. So it could be either an ebb tide or a flood tide. So we're either filling the tidal basin or emptying the tidal basin. So we have our formula from the previous slide. If I put in now the constants that we know, the density of seawater, we can come up with the energy available in units of kilowatt hours is 1.397 times 10 to the third S sub r squared. And in the units here now, the basin area is in kilometers squared and R is in meters. Now if we want to go to a year and figure out the energy available in a year, we have to figure out how many tidal cycles there are. There are 8,760 hours per year. It's 12.42 hours per tidal cycle. So there are 706 tidal cycles per year. And so if we want to look at generating on both the flood and the ebb tides annually, we can multiply then 2, so that's the flood tide and the ebb tide. We're recovering on both. Times the 706 cycles times the energy available per cycle, we come up with 1.97 times 10 to the 6th then S sub r squared. Now this is a lot of idealization, and so it's not realistic that we'll actually recover this amount of energy. So one has to incorporate some utilization factor to account for how much of the potential energy we can recover. So there are some values available. So for single basin systems, so that's there's only one tidal basin, and that's the prevalent type. If we capture energy only on a single tide, so typically the ebb tide, but could be the flood tide as well, but just one, we have the energy recoverable from a single tide is 0.44 times 10 to the 6th SR squared. And if we have a double tide system, so this includes capturing energy on both the flood and the ebb tides, the number increases to 0.67, right? So those are our realizable tidal energy on an annual basis. Now, if we want to look at the power available, we can take the energy and divide it by the time over which that energy is released. So if we start off with our idealized energy and divide by the tidal period, 6.2 hours for a single flow, so the ebb or the flood, and we get 0.226 times 10 to the third SR squared. Now in practice, only something in the order of 25 to 30% of that can actually be achieved, and so the average power then is a reasonable formula for the average power is 0.056 times 10 to the third SR squared. So this takes the more conservative value, 0.25 of the total available. Okay, now just before we look at an actual system, we need to know something about turbine characteristics. So these are low head turbines, typically a Kaplan type turbine, and the graph here shows representative characteristics. So there are two things plotted here. The first one is the water volume flow rate through the turbine, so that's the green line, the blue line, pardon me, which is shown here. So in meters cubed per second. And the other thing plotted here is the power output of the turbine generator set. So this green line shows the power output, the axis is here. And both of them are plotted as a function of the head, the pressure head available to drive the turbine. So you can see that this particular turbine is rated at, develops its rated power at 3.7 meters head, and at heads higher than that level, it's necessary to decrease the water flow rate then to prevent overpowering the electrical generator, right? So the power is limited once it reaches the generator capacity, basically. So a couple of things to take away from this particular graph is obviously the power output depends strongly on the head. So that's an important characteristic, and the generator rating limits the output, which we talked about, and the most important one of all is that there's some minimum head required. You can see for this particular turbine only 0.7 meter heads, minimum 0.7 meter head is required to get the turbine to operate properly, right? So that plays out in our tidal barrage operation. So let's move to the tidal barrage operation. So now with the basic understanding of the turbine characteristics, we can look at the ebb generation operation. So this is the simplest system. We have water flowing into the tidal barrage through the sluice gate on the flood tide, close the sluice gate, and then you allow the water to flow back out during the ebb tide. All right, so the graph shows a complete tidal cycle of 24.84 hours. And so the blue line represents the sea level, so this is the tide itself, and you can see it's a diurnal tide with 2 highs and 2 low tides during the day. The red line shows a hypothetical basin height to illustrate the operation of the ebb generation system. Now, what drives the turbine is in fact the head across the turbine, and so the head is essentially the difference between the basin height and the sea at a particular time, right? And so the green line down here is that difference. So this green line is the head available to drive the turbine. And I've also included on here this dashed green line, which represents the 0.7 meter minimum head before the turbine will operate. And so you can see that only during certain periods is the head available to drive the turbine above the minimum required for it to operate. In fact, we generate during the period 2 hours 2 to 7.4, so from here to here, and then also from 14.4 to 19.8, so the second period over here. So in total, only 10.4 hours of the 24.84 do we have power generation, so about 40% of the time. Moreover, in this particular example, even though the tidal range is 6 meters, so from here, the low tide to the high tide is 6 meters, in fact, the maximum head available is only about 2.5 meters. Now, we could increase the head available by reducing the flow rate, so that would slow down the flow out and keep the basin height higher, so this would come down like this, for example. But if we reduce the flow rate, the net power available is a product of flow rate and head. So there's a very complex optimization to be done here to maximize. What you want to maximize is the energy output, the power integrated over the time that power is actually being produced. Right? So the graph here simply shows one example. It's not an optimized example, but just to give you an idea of how the process works. And what this shows us, of course, is that sizing the turbines, determining the flow characteristics, how fast this water level falls off, is a really important iterative exercise that has a big impact on the overall energy output of the barrage system. Okay, now this was for the simplest case, ebb generation, and so clearly generation during both the flood and the ebb tides is much more complicated and indeed requires special turbines and additional controls. So it's an open question as to whether or not the increased electrical output generated by the dual tides justifies the additional cost of the more complicated equipment. Cost includes, in this case, not only capital costs but also operating and maintenance costs. So each situation would have to be examined in detail to determine what works best. So now, with a basic understanding of tidal barrages, we are in a position to look at some operating examples, and we'll do so in the next lecture. To conclude this lecture, let's summarize some key points. First of all, the basic concept of a tidal barrage is it essentially closes off a bay or a tidal estuary to capture flowing and/or ebbing tides, flooding and/or ebbing tides. So we can make an estimate of the annual energy output for a single basin system. We have an equation for the single tidal flow, so capturing power just on the ebb or the flood tide, or for a double tidal flow, so capturing power on both the ebb and the flood tides. You can see those numbers 0.44 and 0.67 times 10 to the 6th s sub r squared respectively. And finally, we have an equation for the average power available, which is 0.056 times 10 to the 3rd s sub r squared. Please try the questions that follow to aid your understanding of tidal barrages.